All right, guys, so we're on the last page, the check your understanding for part 3. So this is kind of the majority of questions that you can expect to be actually asked on a test. I am going to ask you to make a scatter plot using StatDisk on your homework, but on a test, it'll be more like you are given the output, and then we're going to work based on that. So the problem here says some data were collected on the weight of a male white laboratory rat for the first 25 weeks after its birth. So that kind of gives us an idea of how far our data is reliable. So first 25 weeks would mean from 0 weeks to 25. Going outside of that would be extrapolation. So keep that in mind. It says a scatter plot of y equal to weight in grams and x equal to time since birth in weeks. So if x is 0, that would mean it was just born. If x is 25, that means it's 25 weeks since it's born. Makes sense. And then its weight is given in grams. So, I'm already kind of thinking this is probably a positive relationship. As the rat gets older, it gets heavier. So it's growing. So it says that scatter plot showed a fairly strong, so if I'm thinking about the correlation value, R is probably pretty close to 1, positive linear relationship. I was right about positive, and the scatter plot shows that it's linear. Remember, the correlation value R cannot show linear. That's why we have to look at scatter plot. Correlation value assumes that it's linear. And then it says, here's the regression output from statdisk.org. So again, if I had actually entered the data, I would get something like this, right? Which has quite a few things, but I just took out the chunk that is actually the regression results, okay? So I'm looking at the regression results here. Again, notice this was the data from sugar and calories. I'm just giving you an example of the type of the StatDisk output. These are the actual regression results for the situation we have here now with time since birth and weight. Okay, so again, it points out our y-intercept. This time is 100.0248. That's our B naught. And then we have our slope, B1, is 40.00136. That's what we're going to plug in. Now, again, we'll probably round to 2 decimal places. That's reasonable. So let's construct the regression equation. Now, I know it's tempting to just go ahead and put y hat here, right? But again, we want to put this in context. So the context for y is weight. So we will say weight. Weight hat is equal to the y-intercept, which is 100.02 plus, because the slope is positive, and then let's fill in B1, our slope. Actually, 40.00 is just going to be 40, so I'm going to leave it at that. 40, and then it's tempting to put x, but again, I want to replace x with what x actually represents, which is time since birth in weeks. So I'm just going to use time. So 40 time, weeks, yeah, time I think is fine. 40 times the time. I probably could have put weeks there. It doesn't matter. So weight hat is equal to 100.02 plus 40 times the time. Okay, so now let's interpret the slope of the regression line. So here's my slope, right? I want to interpret that. So remember that interpretation sentence says for each additional x context. So the x context here is weeks in time since birth. So let's say for each week since birth, comma, let's look back at that sentence again. For each additional x context, the predicted y context increases or decreases by the slope. So for each week since birth, the rats, I'm going to try to really put it in context, the rats predicted, remember that word predicted is so important. The rats predicted weight, that's the y context. Now, again, the slope is positive, so it increases by what the slope is, 40, and then put it in units for the weight for the y context, so 40 grams. So for each week since birth, the rat's predicted weight increases by 40 grams. I can't say that it for sure increases by 40 grams, but that's the prediction. Okay, so then does the value of the y-intercept have meaning in this context? Because sometimes 0 is not a reasonable value for X, the Y context might not have meaning. But in this case, an X value of 0 would mean the rat is 0 weeks old. It's just been born. And in that case, it does make sense. The rat is going to have weight when it's born, so we can predict that weight when it's born. So yes, when a rat is born, comma, it is 0 weeks old. Okay, that's what we're talking about. And when a rat is born, slash, I'm going to change this from comma to a slash. So when a rat is born, slash, it is 0 weeks old. Let's go back to that sentence again. This is the y-intercept prediction. So when x equals 0 in context, I've already got that. When the rat is 0 weeks old, the predicted y context, so the predicted weight, is the y-intercept. So the predicted weight is equal to that y-intercept, which is 100.02 grams. Again, using the unit of measurement for weight. Okay, so then it says predict the rat's weight at 16 weeks old. So we need to use our regression equation up here. So I have weight hat is equal to 100.02 plus 40 times my time, and my time here is 16 weeks that I'm plugging in. Okay, so let's see what we got for the predicted weight. All right, I have 100.02 plus 40 times 16. 740.02. I think we can go ahead and run that to just 740 grams. 740 grams. Okay, so then it says calculate and interpret. Notice it says and interpret the residual. Remember, the residual is that actual minus predicted if the rat weighed 700 grams at 16 weeks old. Okay, so they are telling us the actual here. This is my actual, and I just found that this is my predicted weight. So to find my residual, I want to do actual minus predicted. Residual equals actual minus predicted. So that is 700 minus 740, which I can tell is negative 40 grams. Okay, so I've done the calculation. I'm gonna underline that in purple. I've calculated. The calculation is negative 40 grams, but now I also have to interpret. Don't forget that part. Okay, so let's go back up to that interpretation for the residual. It says the actual y context. So the actual, let's see, what's the y context? Weight. The actual weight was, and then I use the residual, so was 40. Notice I'm not going to use the negative part of this because the negative is going to tell me whether it was higher or lower. So the actual weight was 40 grams lower than predicted. Just make sure that's right. Okay, the actual weight was, our residual is 40, so 40 lower because the residual was negative, lower than predicted for, and then we have to put our x in context with the value we used. So then predicted for a rat at 16 years old. For a rat at 16 weeks old. I put my x in context and gave the value. Okay. All right, so our prediction was actually higher this time. The actual was lower than the predicted value. So again, the interpretation here is this part, okay? I have to have that interpretation as well. Okay, finally, should you use this line, this regression line, to predict the rat's weight at 2 years old? Okay, let's put that in terms of weeks. 52 weeks in a year, so 2 times 52 is 104 weeks. Use the equation to make the prediction and discuss your confidence in the result. Okay, so we can go ahead and make the prediction. So here, weight hat is equal to 100.02 plus 40, but this time times 104 weeks. And let's see what we get. 100.02 plus 40 times 104 weeks. All right, we get 4,260. 4,260.02 grams. Let's actually convert that to pounds since it tells us there are 454 grams in a pound. I need to divide that value by 454 to see how many pounds that is. 9.38 pounds. Holy cow. So they're saying that if we that they're predicting that a 2-year-old rat would weigh 9 pounds. That is a huge rat, and praise Lord, there are no 9-pound rats around us, right? I really, really hope that that prediction is wrong. So it says discuss your confidence in the result. Why is this so large? Well, we're assuming that the rat follows the pattern after that first 25 weeks. Now, 25 weeks is only about 6 months, right? It's like half the year. So we expect the rat to grow for a considerable amount of time and then stop growing, right? It becomes an adult rat, just like adult humans, and they stop getting bigger and bigger. So this regression line does not account for that, right? It only goes up to the first 25 weeks. 104 weeks is way beyond that. So this is extrapolation. Okay, so we want to discuss our confidence in the result. And we also, it says, should you use this line to predict the rat's weight? No, we shouldn't use this line to predict the rat's weight at 2 years old. 2 years, or I'm going to go ahead and put in there 104 weeks old. Because our sample data is only from the first 25 weeks. This is extrapolation, and we cannot trust the prediction. Again, thank goodness, because we do not want any 9-pound rats running around. Okay, so that is it for the IS number 22 notes. Again, be looking for the homework assignment to be posted as well. It's not going to be coming from your textbook. This is another type of assignment, just like these tests that we've been having. You don't actually have to print it out. You just have to make sure to label the problem numbers if you work it on a blank piece of paper. Okay, let me know if you have any questions.